start with number 5. It says that 800 Newton billboard worker stands on a 4-meter scaffold weighing 500 newtons and supported by vertical ropes at each end. How far would the worker stand from one of the supporting ropes to produce a tension of 550 newtons in that rope? We have a scaffold. And scaffolding itself weighs 500 newtons. And we'll assume that occurs at the center of mass. 4 meters across. And let's just say that our 800 Newton billboard worker is standing at some position here. We don't know exactly what that is, but we want to find, in fact that's what we want to find, is how far is the worker from one of the ropes. So we're going to say that the worker is some distance x from one of the ropes. And that will produce a tension of 550 newtons in that rope. So this tension 1 is 550 newtons. We'll have a tension 2 over here. So we want to find x. Let me redraw this 3-by diagram for the scaffolding. We've got its weight, 500 newtons here. We've got the worker. Newtons here, distance x away. The 500 newtons is a distance 2 meters away from this end. We've got tension 1, which is 550 newtons, and tension 2, which we don't know. I want to find x. I do. Yeah, that sounds like a good idea. Real good idea. Let's choose this spot where tension 2 is acting on the scaffolding. I'll call it point B. I call this point A over here. If I choose that spot, I'll eliminate tension 2 from torque consideration. I didn't know what tension 2 was anyway. So I eliminate that from consideration so I don't have to worry about it. And now I'm going to calculate the torques about point B here. All right. Now if I do a little torque diagram on that, it might look something like this. Here's point B. Here's 500 newtons. Now that is 2 meters away from point B. And that 500 Newton force is trying to make this rotate counterclockwise, which would be a positive torque. Let's try to make it go this way. That'll be a positive torque. I've got the worker, which is 800 newtons. That also, well, the moment arm for that 800 newtons is what? 4 minus x. So we take the whole 4 minus the x, and that'll be 4 minus x.
I got a question.
Yeah.
Okay, I see.
And that's also trying to make this rotate counterclockwise, so that's also a positive torque. Try to make it go that way. And then I have this T1, 550 newtons. And that has a moment arm about point B of 4 meters. And that's trying to make it rotate clockwise, which would be a negative torque. And as a result of these three torques, two of them positive, one of them negative, if I add them all together, I get 0 because the scaffolding is not rotating at all in reality. So no net torque. So summation of all the torques about B should be 0. And I have 2 meters times 500 newtons plus 4 minus x meters times 800 newtons minus 4 meters times T1, which was 550 newtons, and equal to 0. I have a bunch of numbers in there in x. I can solve for x. So I'll say that 4 minus x times 800 is equal to 4 times 550 minus 2 times 500. Or I could say that 4 minus x is equal to 2,200 minus 1,000 divided by 800. Or x is equal to 4 minus all this stuff, which is going to be 1,200 divided by 800. It's going to be 1.5. This is going to be 2.5 meters. Answer is C. So even though I drew it as if x were a lot closer to this end, in order to make this work, 500 newtons on this tension, we actually have to go over halfway, a little bit over halfway on this side. X was arbitrary, so they allowed us to do that. Neat. Anything else on that page that was interesting? Take a look at problem number 12. If a uniform 100-pound beam is held in a vertical position by a pin at its lower end and a cable at its upper end, a horizontal force, magnitude P, acts as shown in the figure. If P is equal to 75 pounds, what is the tension in the cable? So we're going to have to deal with foot-pounds, feet, and pounds, but everything else is the same. I want to find the tension in the cable. Something like this. This is a 30-degree angle. And we have P here, which is 75 pounds of force. This distance here is 5 feet. And this distance is 3 feet. And the beam itself weighs 100 pounds. So, again, we're going to treat it as if that weight, we're acting at the center of mass of the beam, which would be right in the middle, right there. We have a force of 100 pounds coming down due to the weight of that beam, straight down through the beam like that, acting at the center of mass. And the question is, what's the tension in the cable? Let's do a free body diagram of the beam. I'll look just at the beam. I got this force P going to the right here. I've got this weight force coming down like this, 100 pounds. I've got a tension force coming down this way. And this angle right here will be 60 degrees. This angle right here would be 30 degrees. That tension force. I've got some kind of reaction force at the ground here, at the pivot. I don't really know which direction that reaction force is, but I know it has a vertical and a horizontal component, and the vertical component most likely will be going up, so I'm going to just call that V. And I'm not really sure which way the horizontal component is going to go, because I've got a P force going this way, and I've got a component of the tension force going that way, and I don't know which one is going to need the extra balance. So, for lack of a better reason, I'll just put the horizontal force to the right like that. And if I ever try to calculate what that horizontal force is, if I came up with a negative answer, all that would mean is that I assumed the wrong direction. That it actually was the same magnitude force. Okay, we want to find out what T is. What should I do? I've already done the free body diagrams. I can't answer that. Use the pin, because if I choose this pin, which I'll call A, I eliminate two things I don't know, the V and H from consideration for torques. And for that matter, I also eliminate the weight, because the line of action of that force goes right through that pin, and it has no moment arm about that point. So that's a great choice, because I've eliminated three forces right there. Right? And for that matter, I also eliminate one component of the tension. The component that's coming down, which would be a T sine 30. If I were to break this tension up into two components, I could have a T sine 30 coming down and a T cosine 30 going across. So I could break the tension up into two components. The one that's coming down would be going right through that point A as well and have no moment arm, so I eliminate that from consideration. So point A is a great choice. And now, as far as torques go, this is what it looks like. I got P. Let me give myself enough room. I got P at 75 pounds, which is 5 feet up, going to the right, and I have a T cosine 30 acting at the top with a moment arm of 8 feet. T cosine 30 is trying to make this thing rotate counterclockwise. That's going to be a positive torque. The P is going to try to make this thing rotate clockwise. That's going to be a negative torque. And as a result of those two torques, it won't rotate at all. So we'll have a net torque of 0. All right, so let's try that. See if we got enough room here. That, let me go over. Summation of all the torques about A should be 0. And we have T cosine 30 times moment arm of 8 feet minus P times moment arm of 5 feet. That should equal 0. Let's solve this with T. So we have T times 8 cosine 30 equals 5 times P, which is given as 75 pounds. Or the tension in that cable will be 5 times 75 over 8 cosine 30. Just get 54.1 pounds. The feet canceled out. So we ended up with foot-pounds on top, feet on the bottom. Those canceled out, and we ended up with pounds again. You know, another way I could have done this when I was looking at this about point A is I didn't have to break up T into its components. What I could have done is just extend the line of action of T. It's coming down here at a 30-degree angle. And so if I just extended that line of action, found the shortest distance to that line of action, so such that it was perpendicular to that. This would be a 30-degree angle. Then I could use the whole full force of T times that shortest distance. That would be the moment arm for the full T force. Right? And that shortest distance, see, if this is 8 feet for the hypotenuse of this right triangle, and this distance right here is going to be 8 cosine 30. So that's my moment arm. So my torque due to T is going to be T times 8 cosine 30. Which is what we had. Right? We broke T up into components and did it that way. But we could have done it this way. I'm feeling better today, so you can see that I'm a little bit more excited about this. This is good stuff. The static stuff is it's fun. That's important. It's, like I said, it's the most important thing that we're going to do in this semester. So it's important that you master it. Anything else you might want to look at? problems in the book are actually good for this too. But, we haven't done too many things in the book. At least when I come out with a sample test, I'll put a few new problems in there. Maybe with some furry animals. Figure out a way to do that. Okay, I'm ready to go on to something new, or slightly different. Anybody here watch the History Channel? Did you watch it last night by any chance? There's a series on the History Channel called The Universe, and it's the second season. Last season they talked mostly about the solar system. They started looking at each of the individual planets in the solar system. One last night about gravity in general. Gravitational waves and Einstein and Newton and everything. And this so happens that that's what we're going to talk about today. So there was a show last night, but it came to be in the second season now. They're going to be more specific about different aspects of the universe. And last night's show was called Gravity. So they're just talking wholly about gravity and a lot of the neat things that I like to mention about gravity. They were saying in that show too, so that was kind of neat to see it in one little show like that. I probably should just show you the video, but I guess I think I'd rather tell you myself. So today we're going to talk about gravity and how it might impact our solar system. First thing is to introduce, right off the bat, Newton's law of gravity. It's a law that Newton first proposed in his Principia, and it's something that could be derived just by experimental observation. You notice that you have two masses, and that if you increase the mass of one, the force between those two masses would increase proportionally. If you increase the mass of the other, the force between them would increase proportionally. And if you increase the distance between them, the force drops off by that distance squared. And this force is attractive, so that's what the minus sign means. And it's attractive between every mass in the universe. So every mass in the universe has an attractive force on every other mass in the universe. So if I had these two objects, right now there's an attractive force between those two objects. And there's a force that's pulling this one towards this object and pulling this one towards that object. And it's proportional to this mass, it's proportional to this mass, and it's inversely proportional to the distance squared. Oftentimes, I'll kind of, at least in a magnitude sense, ignore the negative sign because that's a matter of your situation. I mean, the negative sign means attractive, but in a mathematical sense, what is a negative force? Well, I mean, if I had two objects like this, for this object, the force is in the negative x direction. But for this object, that attractive force is actually in the positive x direction. So really, in calculating this force, you probably just want to figure out the magnitude, g mass 1, mass 2 over distance squared, and then look at the situation and then figure that that force must be attractive, and then get the direction from that result. G out front is a gravitational constant, universal gravitational constant, and its value is 6.67 times 10 to the minus 11. 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. It kind of flows off the tongue. 6.67 times 10 to the minus 11. It's easy to remember. What's that supposed to say? Do you have to? Yes, you have to. Because you might be walking along and you might think, what's the gravitational attraction between that object and that object? If you do it in your head, you're going to have to know 6.67 times 10 to the minus 11. Here's some beautiful features of this law. This gravitational force acts from a distance between the two particles regardless of the medium that separates them. So, for instance, one reason we're talking about gravity is the application for the universe, and in particular the solar system. The reason the Earth goes around the sun is because of the gravitational attraction between the two bodies, the sun and the Earth. And so the sun kind of keeps the Earth pulled in, and the Earth will go around the sun due to that gravitational attraction. The force of gravity is the centripetal force that keeps the Earth moving in a circle. Now it acts from distance so that if something came in between, I need a third hand here, like the moon. Let's say the moon is going around the Earth like this, and from time to time we have a solar eclipse. So from time to time the moon will be exactly between the Earth and the sun. When the moon does that, it does not shut gravity off. Right? So it doesn't block gravity, so to speak, because now the sun's acting on the moon and not the Earth. No. So if something comes in between, the gravitational force between the sun and the Earth still is in effect. So it acts at a distance no matter what comes in between. Which is a good thing. So we don't go flying off into the solar system. The force increases rapidly with increasing separation. It falls off as the distance r squared. You have a gravitational force of attraction from the Andromeda galaxy. All right? The Andromeda galaxy has a lot of mass, a lot of stars, billions of stars, and a black hole as well. And that has a lot of mass, and it's got a force on you, but it's not a force to worry about because it's so far away. Right? It's 2.9 million light years away. So because it's so far away, that's a fractional, minute force on you that it's not anything to worry about. The gravitational force is proportional to the mass of each particle. You have a force on you from the Earth. When we treat the Earth's mass as being located at the center of mass, the center of the Earth. So the distance between you and the Earth is the radius of the Earth. And mainly that force is large enough because the Earth is so massive. And you got your mass. Ultimately, say for somebody like me, that force of attraction between me and the Earth is 170 pounds. Right? Which is really pretty small when you think of it. Because the Earth is incredibly massive. Right? 6 times 10 to the 24 kilograms. The gravitational force of a uniform spherical mass distribution on a particle outside the sphere is the same as if the entire sphere were concentrated at its center. In plain English, if you have a sphere, we treat the mass of that sphere as located at its center mass. So even though there's a distribution and there's some mass near the surface and mass over here, we treat this mass as if all of its mass were located at its center mass. So with that previous example that I just said about the Earth, when I try to calculate that force between me and the Earth, I have to put the Earth's mass at its center. And then the distance between us would be the radius of the Earth. And if I were trying to calculate the force between the Earth and the Sun, I would treat the mass of the Sun at the center of mass of the Sun, the center, and the mass of the Earth at the center of the Earth. So I wouldn't worry that there are some parts of the Sun that's closer than that, and some parts of the Earth that's closer than that because of the curvature of both. I treat them as point masses at their center of mass. All right, so let's try this law out with an example. Here's a problem. What's the force of attraction between Ben, who's 75 kilograms, and Jen, who's 55 kilograms? They are 1 meter apart. Ben and Jennifer Lopez, they used to go out, right? A long time ago. But you see it.
He needs to revise them.
I think I have revised them. All right, there we go. Ben and Jen. If they are 1 meter apart, if we were to calculate this, we have our G constant, 6.67 times 10 to the minus 11. Ben is 75 kilograms. Jen is 55 kilograms. They're 1 meter apart. So we find that force is 2.75 times 10 to the minus 7 newtons. 2.75 times 10 to the minus 7 newtons. Not enough for them to spontaneously collide, right? Because the air friction would be enough to kind of hold off that force, maybe. Actually, in that program last night, we came up with a good example, which I think I'm going to use from now on. They said that if you went out into deep space and you had 2 dice, which I didn't bring the dice in, but if you had 2 dice and you placed them 1 centimeter apart in deep space, free of any other gravity or other forces, and you just let go of them right there, that they would be attracted to each other by their own mass, 1 centimeter apart, and in the course of 1 hour, they would move together. So you place them 1 centimeter apart, and after 1 hour, they would actually move together. That's kind of neat. You could actually figure that out, because you could figure out, if you knew the mass of the dies, you could figure out the force that's between them, divide that force by the mass to get the acceleration, and then use your kinematics, knowing that the distance they have to go is 1 centimeter. Use your kinematics to calculate the time it would take for one of those to cover 1 centimeter. Or half a centimeter, I guess if one's been that way. Take a look at this problem. 3 interacting masses. 3 uniform spheres, mass 2 kilograms, 4 kilograms, and 6 kilograms, are placed at the corners of a right triangle. Calculate the resulting gravitational force on the 4 kilogram mass. What we can do is look at the separate forces and then add them together vectorially. So we have a force between the 6 kilograms and the 4 kilograms. And we have a force between the 4 kilograms and the 2 kilograms. And we'll calculate the magnitude of those forces and then treat them as vectors, attractive forces. So if I look at the force between the 4 and the 2, I'll have G, mass 4, mass 2, over the distance between them squared. And it looks like that force is totally in the y direction. So I'm going to give it a J unit vector. 6.67 times 10 to the minus 11. 4 kilograms times 2 kilograms over 3 meters squared gives me 5.93 times 10 to the minus 11 newtons in the J direction. So even though it's an attractive force, I could actually say that that force is in the positive J direction. So that's why I didn't put the negative sign in there. I just calculated the magnitude, looked at the situation, and figured out the direction of that force. The force between the 4 and the 6 would be G times 4 kilograms times 6 kilograms over 4 meters squared. And that's in the negative I direction. So that's a negative 10 times 10 to the minus 10 newtons times I. So I have a net vector force of a negative 10I plus 5.93J times 10 to the minus 11 newtons. And I can figure out the magnitude and direction of that force. Magnitudes, in this case, the two components are at a right angle to each other, so I use the Pythagorean theorem, square both components, add them together, get the square root. And I get magnitude is 11.6 times 10 to the minus 11 newtons, and the direction is the inverse tangent of the y component over the x component, 30.7 degrees north of west. So it would come up like that. So if I had this situation, at least the initial movement of this 4 kilogram mass would be along that red arrow, where it would feel this total force and would start to move in that direction. Well, weight is a force. It's a force of gravity, like I mentioned. My weight is due to the force of gravity between me and the Earth. So I would say that my weight, mg, m little g, 9.8 meters per second squared, is equal to, using Newton's force of gravity, 6.67 times 10 minus 11, the mass of the Earth times my mass over the distance between us, the radius of the Earth, squared. If I look at this, my mass is on both sides of this equation. So I can actually cancel that out. And I get that little g, that constant that you all know and love right now, at 9.80 meters per second squared, sometimes 9.78 meters per second squared if you're in Alabama. That is equal to our gravitational constant, 6.67 times 10 minus 11, times the mass of the Earth, 6 times 10 to the 24 kilograms, over the radius of the Earth, 6.4 times 10 to the 6 meters squared. That's where our little g comes from. 9.8 meters per second squared is related to the physical values of the Earth. The mass of the Earth over the radius of the Earth squared times a constant, a universal constant. So if you found yourself on a different spherical body, you would have a different value of acceleration on that body based on the mass of that body and the radius of that body. And another feature of this is that this is true for everybody, right? Because when we got to this point, we crossed out our mass. So this is true for everything. Everything on the Earth. All things fall at the same acceleration on the Earth. That's what Galileo found. Right? that things that are more massive fall at the same rate as things that are less massive. Of course, if you put a feather out there, it will have to deal with air friction. But if you put it in a vacuum and put it under the same gravitational attraction, it will fall at the same rate. So if you're standing on the Earth, let's say you actually weigh 180 pounds on the Earth. If you travel to the moon is a lot smaller than the Earth. Its radius is about about 1/2 the radius of the Earth. So you're a lot closer to the mass of the moon if you go to the moon, and that would have an effect of increasing the gravitational attraction between you and the moon. The problem is the moon is so much less massive than the Earth. It's about 1/80th the mass of the Earth. So those two kinds of effects kind of mitigate each other, and you would find that your weight on the moon is only 1/6 your weight on the Earth. So if you weighed 180 pounds on the Earth, you would only weigh 30 pounds on the moon. So go to the moon. Yeah, this is what I call the Dr. Golben weight plan, diet plan. If you want to lose some weight, the easiest way is to jump onto a rocket and travel to the moon. Then you'll lose 83% of your weight. Then come back. Yeah. What I would like to do sometime in the future, when we're going to the moon on a regular basis, when you look at travel plans, and you got Hawaii, and you got Cancun, and you got the moon, right? And the cool thing about the moon, if you go to the moon and playing basketball on the moon, that's what I want to do. So I want to go to the moon and play basketball for a weekend, right? Might lose the ball, yeah. Might go into orbit. But if you go to the moon and you still have the same muscle structure that you have for the Earth, then all of a sudden you're a superhuman powers on the moon, because you can jump incredibly high and decide what you want to do before you dunk the ball. That'd be a lot of fun. You don't want to stay too long, because then your muscle will start to atrophy. Just a weekend. If we use the fact that the radius of the Earth is 6.4 times 10 to the 6 meters, we can find the mass and density of the Earth from this equation. So rearranging the equation, I get the mass of the Earth is our g acceleration, little g acceleration, times radius of the Earth squared over big G. So 9.8 times 6.4 times 10 to the 6 meters squared over 6.67 times 10 to the minus 11 gives us a mass of the Earth at 6 times 10 to the 24 kilograms. And I can figure out the density of the Earth as the mass of the Earth divided by the volume of the Earth. We treat the Earth like a sphere, so its volume is 4/3 pi r cubed. Put in those values, the mass of the Earth and the radius of the Earth, so 4/3 pi times 6.4 times 10 to the 6 cubed, gives us the density of the Earth as 5.5 times 10 to the 3 kilograms per meter cubed. In terms of grams per cubic centimeter, that's 5.5 grams per cubic centimeter, 5.5 times the density of water. Earth is the most dense planet in the solar system. And that's a lot of fun. Anytime that you can figure out stuff about your physical world, that's a whole lot of fun. I don't know if we did the example on our first day, I forget. Did I do the example of going to the beach and calculating the radius of the Earth? I talked about that? All right. So, What's that?
Watching the sunset.
Watching the sunset. So I did that this weekend. Well, I was at the beach. No, I didn't. But I thought about doing it this weekend. And that's something you could do, is go to the beach, calculate the radius of the Earth, and if you did that, you could continue with this calculation. You could calculate the mass of the Earth and the density of the Earth. And so just staying in one spot, making a few simple observations, you can learn everything you need to know physically about the Earth. We want to apply all this gravity stuff to the solar system and beyond, because that's really where it first came into play. And even though this gravity force that we're talking about is evidently really weak in comparison to other forces that we deal with, it's really the force that keeps the universe together. So these weak forces acting at large distances are really what holds us to the sun and keeps the sun in the Milky Way and the Milky Way in the local cluster of galaxies and so forth and so on. So it's what holds the universe together. So we want to kind of see what's happening out there. Well, here's one thing. Suppose you lived in ancient times. Right? So you didn't have television, you didn't have cable, you didn't have the internet, you didn't have computers. I know it'd be terrible. But suppose you lived in ancient times where the best thing to do in the evening was to actually go out and look at the stars. Right? You probably everybody would have better knowledge of what was out there in the stars. I mean, just your common everyday person would have pretty good knowledge of what stars were what and what to expect in different times of the season. A lot more so than we're used to today, because we don't worry about that on a daily basis. Well, ancient observers found that if you looked out at the stars, you would have your bright stars and your weak stars, and there'd be 6,000 stars that you basically could see. But among these stars were what appeared to be brighter stars, and those brighter stars seemed to have their own course of action. That among this background of fixed stars were these bright objects that seemed to move around that background of stars, and they actually had a weird motion. They actually moved against, over the course of days and weeks and months, they moved against that background in the opposite direction of the background was moving across the sky. And from time to time, those objects would do a loop-de-loop in the sky. So they'd be moving along, fine in this direction, and all of a sudden they move back this way, and then they move back this way again. Right? Those were called wanderers, or eventually they were called planets. In the time of Aristotle, just after Aristotle, there was an astronomer, the best astronomer of the day, Ptolemy. And Ptolemy came up with this view of the universe, actually this view of the solar system, that would explain the motion of these bright planets. And what Ptolemy said was, since it was believed that the Earth was the center of the universe, and this whole sky was just one big sphere of light, so to speak, that moved around the Earth, that along this sphere were these planets that were moving along their own little path called a deferent. And on this path, every once in a while, they go through a little circle, and we call that circle epicenter. So you have the Earth at the center of the universe moving like this, the planets going around this deferent, and then doing a little epicycle once in a while. And from our perspective, that would look like a loop-to-loop in the sky. And it's going like this, go back, and then you go forward again. Because we're looking at it edge on. So in this view of the universe, of the solar system, it might look something like this. The Earth is at the center of the solar system. The moon's going around the Earth. And Mercury and Venus are going around the Earth. The sun is the third object, well, other than the moon, so I guess it might be the fourth object, from the Earth, going around the Earth. And then you have Mars, Jupiter, and Saturn. And they're all doing these epicycles at various times. Jupiter is doing them. Jupiter's moving a lot more slowly than the sky, but it's doing the epicycle once a year. And for Mercury and Venus, they would only do their epicycles when we were in conjunction with the sun. So the sun's right there, and as we came into conjunction with the sun, then Mercury and Venus would do their epicycles. All right, so we're in line with them, and that's the only time they do them. This was the first plan, but then as they started plotting the positions of the planets a little bit better, they got more accurate data, they had to add more epicycles. And I'm not going to show you what the final diagram might look like, but you could end up with 5 little epicycles for every little planet. So you got a circle here, and another circle, all to accommodate all the minute calculations for the position of the planet. You almost would need a computer to calculate these positions based on this model, but it could do it. Nicholas Copernicus, who lived from 1473 to 1543, suggested instead that the planets revolve in circular orbits about the sun, and so this was a heliocentric model as opposed to a geocentric model. Helio meaning sun-centered, geo meaning earth-centered. He suggested that the Earth was just another planet, and along with the other planets, we went around the sun. And using this model, he could explain those epicycles in a much easier way. But even with his model, going in circles around the sun, he had to retain at least a little small epicycle for every planet. He published this in the last year of his life when he knew he was dying. Why did he do that? Because, this was considered basically blasphemy. Because it was saying that we were not the center of all things. Right? You say the sun's the center of the solar system, we're not the center of all things, and the church at that time did not like that idea. So he figured he was going to die anyway, so he finally published it. Here's kind of the idea. You have the sun, you have the Earth. Let's say you have an outer planet, Mars, say in opposition. The closer you get to the sun, the faster you're moving around the sun. There's a concept of angular momentum, which we did not cover. Just skip that section. But the objects that are closer to the sun are moving faster. So Mercury goes around in the course of 3 months, 3 Earth months. And Venus goes around in 220 days. We go around in 365 days. Mars goes around in just about 2 years. All right, 2 Earth years. All right, so we're moving faster than the outer planets, so to speak. Let's say Jake is Mars. All right? And I'm on Earth. And let's say Urban is the sun.
Yeah.
All right? I'm coming around, I'm looking at Mars. All right? Right now, you're to my left. All right? As I go around, I'm catching up to you. At some point around here, you start moving, even though you're moving around the sun like this, you start moving from my perspective to the background stars, you start moving to the right. And you were moving that way, right, in general. But now you start moving to the right because I'm catching up to you. So from our relative velocity, and from me looking at you against a background, it appears like you're moving in the opposite direction because I'm catching up because of my speed. And then I pass you. I can't really do this. But then now I pass you, and now you start moving along like you were before in the forward direction. It's a matter of relative velocity and perspective that your background changes as I'm looking at a closer object as opposed to a further object. Right? The net result is that loop-the-loop you see in the sky over the course of several weeks. Right? So if I'm looking at Mars and we're coming upon opposition, then Mars will be there, and I'll start sort of backtracking, and then I'll go forward again. The problem with Copernicus' idea, real small problem, is he assumed circular orbits for the planets. If you assume perfect circular orbits for the planets, then, and you actually calculate the positions well, you still have to put a little epicycle on each planet, because it's not exact. Along came Tycho Brahe, who lived from 1546 to 1601. He made very accurate measurements of the planets over a period of 20 years without the aid of a telescope. He used a sextant, a very large sextant, and he was able to extremely accurately find the positions of the planets in the sky for 20 years. It was the most accurate measurements of the planetary positions for up to 300 years after these were made. So it was the best data possible in that era, and frankly, for 300 years afterwards. Here's a picture of Tycho Brahe. So he was the best astronomer of the day, coming up with the best data. It may be hard to see from this picture, but there's something wrong with his nose. Right? You can see that there's looks like there's some kind of patch over his nose there. You see that? The reason is he had a fake nose. Right? And the reason he had a fake nose is because when he was in math class at the university, he got in an argument with one of the other students over a math problem. Right? And they decided, after arguing over and over again over this math problem, they would meet outside the next day, outside the math department, and they would decide the solution to this problem with a duel. So they met the next day and had a duel with swords, and the other guy lopped off his nose. So I guess the other guy was right. So Tycho Brahe spent the rest of his life fixing a fake nose, and I think he used some kind of putty or something to accommodate his nose. If you get in an argument over a physics problem, I do not suggest that you meet outside the school and solve it with a duel. Solve the problem, have a duel somewhere else, but not outside the school. It might be important enough to do that, but do it somewhere else. More about Tycho Brahe. He had a pet moose. He had a pet moose. And the pet moose was made himself at home freely. So you would walk into the front door of the house and just walk around the house, walk upstairs, do whatever the moose wanted to do. The moose, unfortunately, met his untimely demise when one particular day the moose walked upstairs and found a vat of beer and drank a little bit too much from the vat of beer and tried to make his way back down the stairs.
Are you making this up?
No, I'm not making this up. This is all true stuff. I can tell you more. The story of Tycho Brahe's demise is actually very similar to the moose's demise, but I'm not going to tell you how that happened. You're going to have to search the internet to figure out what happened to Tycho. But one reason we mentioned Tycho Brahe is because he had come up with the best data for the positions of the planets. And like I said, the best data that would be around for the next 300 years. Well, in the last year of Tycho Brahe's life, he took on an apprentice. And his apprentice was Johannes Kepler. Johannes Kepler was sort of a mathematician. And he saw that Tycho Brahe had all this great data, and Kepler, being a person who was a proponent of the Copernicus idea, wanted to take this data to plot the position of the planets and test out the Copernican theory that the planets were going around the sun. So Kepler said, "Can I look at your data?" And Brahe said, "No. The data is mine. You can't look at my data." He had 20 years of accurate data, and he said, "Now this belongs to me." Strangely enough, he died within a year, and Kepler got all the data. Funny. I don't think anybody's ever proposed that Kepler might have been responsible. But we're happy for Kepler because he came up with some stuff for physics. And one of the things was, once he looked at this data, he pored over it for 16 years, and he came up with 3 laws of planetary motion, which were very important to the progression of physics. The first law was planets do not move in circles, they move in ellipses. So the planets move in elliptical orbits with the sun at one of the focal points of the ellipse. If you do this, how did he come up with this? Just plotted the positions of the planets, and he found that they were actually oblong, right? Not circles, but oblong orbits around the sun. And the sun, so sometimes the planets are closer to the sun, sometimes they're further away. Plotted it, got it done. Second law, incidentally, if you do that, if you put the planets in ellipses, you don't have to put any more epicycles in there. So it eliminates all consideration of little epicycles. It explains perfectly the motion of the planets. Law number 2, the radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. So what Kepler was saying is, as a planet moves around the sun, and if you were to look at the area, the slice of pie that it subtends when it goes from one point to another point, that slice of area, that area is always equal for equal amounts of time that the planet is going around the sun. How he came up with this, I'm not really sure, but if you have 16 years to pore over the data and you're pretty smart, you can come up with something like this. And this actually was a very important result. The planets are sweeping out equal areas in equal amounts of time. That means when they're close to the sun, they're moving faster, and when they're further away from the sun, they're moving slower. Kepler's third law was the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. obvious. What does this mean? Saying that the time it takes for a planet to go around the sun, that time squared, is proportional to the distance of the planet from the sun cubed. Basically, that's what it means. Again, how do you come up with this? 16 years of poring over the data, being a pretty intelligent guy, and looking at the data, he figured it out. These were all empirical laws. What I mean by the word empirical, they're all laws based on data. No other reason for these laws. Just that you got the data and these laws fit. Kind of like the Newton's equation. They just fit. They work. No reason for them. Along came Newton, and Newton took these laws and he proved them all using physical concepts. He proved them using his new law of gravity and other concepts of physics like conservation of angular momentum and momentum itself. So Newton came along and said, yes, all right, I can prove this mathematically, and this is the way things should be based on physics. And that's why the Kepler laws were important, because they allowed Newton to think about the solar system. Let's look at these laws a little bit more closely. First law says that the orbits of the planets are ellipses. So here's the sun, there's a planet. The planet's going around in an oblong ellipse, and the sun is at one focus of the ellipse. The other focus of the ellipse may be over here. And why is this so? Why is the planet going around in an ellipse, not a circle? I mean, if the sun is so big and the planet's so small, why isn't the planet just going around in a circle around the sun? And the answer is, the planet does still have some mass, and the sun has some mass, and really the two of them are actually rotating about their own common center of mass. So it's really a two-body system, like a baton, if you will, an offset baton. And actually the sun is kind of wobbling around the center of mass itself, while the planet is going around that center of mass. And the net effect of the sun wobbling around and the planet going around that center of mass makes it look like, if you were to fix the sun with respect to the planet's actually going around in an ellipse around the sun. The reality is that they're actually going around their own common center of mass. Here's one way that you can make an ellipse. You put two focus points down, one constant piece of string, and just kind of outline your ellipse around that. I don't know why I put that in there. Just in case you want to make an ellipse. You learned that, I guess, in second grade. Kepler's second law. A planet sweeps out equal orbital areas in equal amounts of time. We already know the planet goes around in a ellipse. What this is saying is that, say if you took 1 month of time, and the planet progressed from this point to this point in that 1 month, if you were to calculate the area of this slice of pie, say the area of slice A, and then you looked at another month, maybe slice B up there, and you took 1 month, and you were to calculate the area of that slice of pie, those two areas would be equal. And you took a third month, same time period, say C, and you look at that slice of pie right there, that area would also be equal to the other months. So the planet will sweep out equal areas in equal amounts of time. Essentially, it's saying that when the planet is closer to the sun, it'll have to move faster. So when it's closer in, it moves faster, covers more distance, creates more area, or the same amount of area in total in that time. further away from the sun, it moves slower. I'm not going to spend too much time on this because we didn't talk about angular momentum too much, at all actually. But the section we skipped in chapter 11 was conservation of angular momentum. Angular momentum is the rotational counterpart to linear momentum. And just saying that in linear momentum we saw that it could be conserved under certain conditions. Angular momentum is conserved as well. And angular momentum is linear momentum times radius. So if you have a planet going around the sun, it's got a certain amount of angular momentum that is conserved, and that is its mass times velocity times its radius at that point, mvr. So you can say its velocity is its angular momentum divided by the mass of the planet divided by its radius. And if you do a little bit of calculation, if you think about a planet moving some distance dr, which would be its velocity times dt, you're not going to have to know all this, but with a little bit of derivation here, radius is r, so the area is going to be r times velocity dt, and you integrate that over time, or actually in this case we just want the rate, you come up with this. Change of area per time is equal to the angular momentum divided by 2 times the mass of the planet. And all these things are constants. Angular momentum is constant, mass of the planet is constant, so your rate of change of area is a constant. This is what Newton did, and he just basically said that Kepler's second law is just a statement of the conservation of angular momentum. You are familiar with angular momentum in the sense of an ice skater, for instance. When he or she is turning around on the ice, it has a certain amount of moment of inertia, and then they bring the moment of inertia in. When they bring the mass in, they move faster in order to conserve angular momentum. You may be a little bit dizzy. The Earth does the same thing. The Earth's going around and ellipse around the sun. I think my next screen will show this. Here's a planet going around the sun. The planet has a certain amount of mass and velocity at a radius r. So at some point, it's got angular momentum mvr. And at some other point, it may be further away. So say R2 is further away, so V2 is proportionally smaller in order to make that product, MVR, the same constant. So we can say MVR, MV1 R1 is equal to MV2 R2. Masses cancel out. We have your velocity, if you're a planet, your velocity times your distance from the sun is a constant. So as your distance gets closer, you move proportionally faster. The Earth moves faster at certain times than other times. Does anybody happen to know when we are closest to the sun? How did you know that? I heard it somewhere. We are closest to the sun in January. Right? So in January, we are moving faster around the sun. And in July, we're furthest from the sun. Yeah. So it has basically nothing to do with our seasons. The tilt of the Earth has more to do with our seasons. But the closeness of the Earth with the sun has very little to do with our particular seasons themselves. So you're moving faster in January, which means that you are aging less in January, because the faster you move, according to Einstein's theory of relativity, the less you age. So just something. So January is a good month. to finish up the discussion of Kepler's laws. Sorry. Just a couple more slides. Here's Kepler's third law. The square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. In English, it was that the time period it takes for the planet to go around the sun, that squared, is proportional to the distance from the sun cubed. Here's a proof. If we say, the planets are moving in ellipses, but they're very close to being circular. So if we're just making an assumption, we're going to make a crude calculation here. And we just make the assumption that the planets have a centripetal force, and that centripetal force is due to its gravitational attraction. And I would say that the gravitational attraction between the sun and the planet is equal to its centripetal force, mass times velocity squared over r. If I rearrange this, get rid of the mass of the planet, actually, and note that the velocity of the planet is going to equal the circumference of the orbit, 2 pi r, divided by the period of time it takes to cover that. Then I'm going to substitute 2 pi r over t for the velocity, put that in there, and simplify or solve this for period. With a little bit of rearranging, I get this. That the period of time it takes for the planet to go around the sun squared is equal to whatever's in parentheses there times the radius of that orbit cubed. And whatever's in parentheses is 4 pi squared over our g constant over the mass of the sun. What's in parentheses is called the Kepler constant. And its value is 2.97 times 10 to the minus 19, not necessarily a constant that you need to remember. But this is Kepler's third law in mathematical form, and it's another thing that Newton did to prove his third law using just physical concepts, gravity and centripetal force. Note that if you didn't measure time in terms of seconds, and you didn't measure distance in terms of meters, if instead you measured time in terms of Earth years, and you measure distance in terms of Earth-Sun distance called astronomical unit, the Earth takes 1 Earth year to go around the sun, and the Earth is 1 astronomical unit from the sun. So if you put 1 in for t and 1 in for r, then the Kepler constant is 1 as well. In other words, if you measure time in years and you measure distance in astronomical units, then t squared equals r cubed. Well, you could use that for the other planets. You could say, roughly, that if Mars takes approximately 2 years to go around the sun, 2 Earth years, then you could calculate the radius of Mars' orbit by saying that 2 squared equals r cubed. And so I would say, I would take the cube root of 4, which is cube root of 2 squared, and I come up with 1.58. Right? So I would say that Mars is approximately 1.58 astronomical units away from the sun. The actual value is 1.52 because it doesn't actually take exactly 2 years for Mars to go around the sun. It's a little bit less. But we can use this Kepler's third law to actually calculate distances of satellites around their central body. We do that with Jupiter. Jupiter has moons going around Jupiter. And we can calculate the period of time it takes those moons to go around. It takes the moons separate times. Io, which is one of the biggest moons around Jupiter, takes only about a day and a half to go around Jupiter. And Europa takes about twice that time, I think. So we can calculate what their distance is from Jupiter based on the time period it takes when we go around. And if you actually know both, the time and the distance, you can actually use this formula to figure out the mass of the central object. So when you have a satellite going around a central object, the satellite being a lot less massive than the central object, you can calculate the mass of the central object. And this is one way how we know what the mass of the sun is. Because we know how far the Earth is away from the sun. We know it takes us 1 year to go around the sun. We can calculate that the sun is pretty massive at 2 times 10 to the 30 kilograms. I'm going to stop there with the lecture. And the problem set.